All right, chapter 5 is applying Newton's laws now. So chapter 4, we're just learning about Newton's laws, a lot of vocabulary, a lot of concepts, a little bit of math, some problems, but now we're actually taking Newton's laws and putting them to use in this chapter. So the first section in chapter 5 is about equilibrium. So we have two types of equilibrium. There's static equilibrium and dynamic equilibrium. So always static means we're at rest, and dynamic means we're in motion. So if you keep those two things in mind, that will help you a lot. So static equilibrium, it means the object is going to be in some sort of equilibrium but at rest, and dynamic equilibrium means the object is going to be in some sort of equilibrium but in motion. So we're at rest and we're in motion, okay? And then the dynamic equilibrium is going to be, obviously we're in motion, but we're moving in a straight line at a constant speed. That is how the dynamic equilibrium is going to have to play out. So static equilibrium, very easy. Object is just at rest. Dynamic equilibrium, we're moving, of course, because it's dynamic, but the straight line at a constant speed is going to be necessary also. All right. In both cases, in order for us to be at rest, we can't be moving. And in order for us to be moving in a straight line at a constant speed, both cases the acceleration must be 0. Okay? Therefore, if the acceleration is 0, Newton's second law, remember, Newton's second law is that F equals ma, or A equals F over m, as we talked about. But if we use it in the form F equals ma, if the acceleration is 0, then the net force must be 0 also, okay? So for us to be in any equilibrium, the net force must be 0. All right, so now we have this Greek letter sigma that you saw back probably first time that you saw it was on Algebra 2, and then depending on where you've gone from there, you may have seen it again. But the Greek letter sigma is here, and it just basically means that we're adding up a bunch of stuff. So it means the sum of. In order for an object to be in equilibrium, the sum of the components of all of the forces acting on the object must be 0. This is kind of key here. Really, the sum of the forces equals 0, but what we're going to be doing is we're going to be taking all of our forces and breaking them into components always. So if I have just forces acting in the x direction, fine. Just forces acting in the y direction, fine. But if I have a force acting in both the x and the y direction, so like projectile motion problems or something like that, I'm going to be breaking that force into x and y components. So all of our forces need to be broken into components. And then I have all of my forces in the x direction and all of my forces in the y direction. Okay? So we have the sum of the forces in the x direction equal m times the acceleration in the x direction. And if I'm going to be in equilibrium, then they're going to equal 0 because the net force equals 0. Okay? And then if I have the sum of the forces in the y direction and add all those together, then they're going to equal the mass times the acceleration in the y direction. But there's no acceleration in the y direction either because the net force is going to equal 0. So that's going to be the key for us in this section when we're talking about equilibrium, where we have static equilibrium if the thing is at rest, or dynamic equilibrium if the thing is in motion, okay? Moving in a straight line at a constant speed. So we're going to keep those ideas in mind. This is the major concept for the section. So moving on, the strategy for solving equilibrium problems is here. Remember that for equilibrium, like I just said, the net force acting on an object must be 0, meaning there is no acceleration, the object is at rest, so the net force is 0. If the net force is 0, it can't be moving, or the object is moving, but all of the forces add to 0, so there is no acceleration, okay? So, is the object at rest, or is it moving in a straight line with a constant velocity? You got to ask yourself that first, and then from there, move forward. So then, identify all the forces that are acting on the object and show a free body diagram. You're always going to do that because it's going to help you, and then it's going to help you break down your forces into components and so on. So definitely you're going to be drawing a free body diagram always. And then draw your drawings big, okay? Make sure that you have enough room to put all of the stuff in the free body diagram and that you can clearly see everything. So make sure you're drawing those big. Determine which forces you know and which forces you need to solve for. So this is what we've been doing all year long. Draw your drawing and then label what you know and what you don't know, okay? And then solve, of course, and then check that your answer has correct units. You need your units in your answer. Make sure that your answer is reasonable, right? If you got a slug that's moving at 500 miles an hour, that's probably not reasonable. And then make sure that you're actually answering the question that's being asked. Okay, so that's pretty straightforward. We've seen this kind of list of strategy before. Just the new thing is equilibrium means the net forces are zero. Decide if you're moving or if you're sitting still. That's going to be important as well. So here we go. We have our first problem. Now we have whatever it is, okay? It doesn't really matter that it's an orangutan. It could be an elevator hanging from a cable, okay? It doesn't matter here. But here we have an orangutan. Weighing 500 newtons, hangs from a vertical rope. What is the tension in the rope, okay? So the first thing we're going to realize is that we have static equilibrium here, okay? It's just hanging there. There's no motion going on. So we're going to draw our free body diagram, okay? First thing we're going to do is we're going to put our axes. This is just normal axes. There's no tilted axes or anything, right? It's just the normal situation. So now I'm going to put my particle in the middle. This is just the orangutan, right? We're not drawing actual figure here, just the particle. Now, what is acting on this free body? Well, for sure, it has a weight down, and we have the weight. Now, this thing is static equilibrium, so that means there is going to be another force up, and that's going to be the rope tension. Now, the intention here is to make these two vectors equal so that the net force equals 0. Okay? That is a 0. I just made it worse probably, but that's F net equals 0. Now remember, in a free body diagram we want to include the F net and which direction it's going. So because the F net is 0, we said that. Okay? Now the intention on the drawing was to make both of these vectors the same length, and that's it. That's the free body diagram. So now what do we know? Well, we know the weight. It's not drawing. Weight, there we go, is 500 newtons. Why is it doing that? We're going to get there. Now it's not drawing at all. Still not drawing. Come on. Okay. So 500 newtons. And then the tension, the other force that we have here, is what we're looking for. Okay, now the weight is actually in the down direction, right? So since I put a vector on there, actually I want to erase that vector. I don't want that, and I don't want that. Okay, the reason I'm putting that, erasing that, is because when I wrote 500 newtons there, I don't want the negative sign. I just want to call it 500 newtons, okay? And then the tension, I just want to call it whatever it is here. If I put a vector on there, then I got to call it negative 500 newtons. I just want to call it 500 newtons right now, okay? Now, what I'm going to do is I'm going to say the sum of the forces in, since this is up and down in the y direction, equals, okay? Now, I'm going to write the tension, and this is in the up direction, so that's a positive tension. And then we have the weight, and that is in the down direction, which resists the up positive motion. So I'm going to write minus W. So I'm putting the sign there to tell me that it is down, right? And then because this is not in motion at all, normally F equals ma. Because it's not in motion, I know that the F net is equal to 0. So the sum of the forces here that I have written down equals this, all right? Now equals mass times acceleration, but there is no acceleration, so it's going to equal 0, all right? So now that I have all of that, I have tension minus the weight equals 0. So I'm just going to solve for tension. I have T equals, add the weight to both sides, and I got T equals W. So tension equals the weight. And now I know that the weight is 500 newtons, so tension equals 500 newtons. And because that's a positive value right there, I know that the tension is actually going up. So this makes sense that I got a positive 500 newtons. All right? And that's why I did not put any sign on this right here. I took care of the sign here when I was doing the sum of the forces. So it's really important actually that you pay attention to what the signs are, and that when you do the sum of the forces, you make the signs speak for the direction that the vector is pointing in your free body diagram. And then the signs will work out for you when you get your answer, and you'll be able to check to make sure that the sign matches the direction that it was supposed to be going. All right, so we move on to the next problem. We have a wrecking ball hanging from a cable. You should be able to visualize that. It weighs 2,500 newtons hanging from that cable. Prior to swinging, it is pulled back to a 20-degree angle by a second horizontal cable. What is the tension in the cable, it says. Now, there probably is a bit of a typo here. It should say in that cable or the second cable or something like that. But the intention here is to be meaning that second horizontal cable for the cable that we're trying to find out the tension for, okay? So now, let's draw a picture for that. So we have the wrecking ball, and then we have it's being suspended by this cable here, okay? And then it's being pulled back and then held by this second cable, okay? Now maybe it's stayed to a wall or something like that, we don't know, but it's being held back by this second cable, okay? It says pulled back to a 20-degree angle, so that 20-degree angle is this right here, okay? So this is 20 degrees here. All right, so now that we understand hopefully this picture, we're going to make our free body diagram based on that. So there's no need to tip axes here. We just draw our free body diagram. We're going to put our wrecking ball right here in the center. And then the question is, what forces are acting on this figure, okay, on this wrecking ball? So obviously it's going to have a weight to it. We have the 2,500 newtons. We don't care about that right now. We're just drawing a free body diagram. So here's the weight vector down. Then we also have, of course, the tension in the cable that's holding it against the wall or whatever, drew it back anyway. And then we also have the tension in the cable that's holding it up into the air in the first place, okay? Now we know that this is a 20-degree angle right here, so we want to put that on there. Okay, now you should be trying to draw your drawings big enough that you're able to put all these details in the drawing. Mine's a little bit too small. I'm having a little bit of trouble putting all that on there, especially on my computer screen here. Now, we also know that this ball is not moving. So all of these forces should be adding to 0. So I need to put that on here. F net equals 0. All right, now we have two forces, the weight vector and this force over here that I haven't labeled yet. This is a tension force. I can call it T1. And this force here that's holding the ball up into the air, I can call that T2. So we have three total forces here, but two of them are acting already along an axis. So the weight vector is acting along the y-axis, T1 is acting along the x-axis, but T2 is acting in two different directions. So we are going to want to break that into components. So we're going to break T2 into an x component. I call that T2x. And we're going to break T2 into a y component. Now, on the free body diagram, it would make sense to draw T2y along the y-axis. But for us, geometrically, it's going to make more sense for us to draw T2y right there. Because now we form this right triangle, the right triangle angle is right there, and now we have this 20-degree angle sitting up here, and a right triangle, we can use some right triangle math to figure out the length of T2x and T2y. In other words, the amount of weight in the y direction, or the amount of tension in the y direction and the amount of tension in the x direction from T2, okay? So that is critically important that we do that for every single vector that is directed along an angle that's not directed along an axis already, okay? We want to do that. That's very important. All right, so now what do we know? Well, we know that the weight is 2,500 newtons. We know that the sum of the forces in the x direction will be T1, but that is going against the positive, so we're going to write negative T1. Oh, here I go again. Okay, good, it's still writing. Negative T1, and then we have a positive T2x, so plus T2x, and that's it. That's all the forces that are acting in the x direction. Now, this ball is not moving, as we know, so that would equal ma, but acceleration is going to be 0, so equals 0. Now we can solve for T1 or T2x, it doesn't matter. Either way, if I add T1 to both sides, I have T1 equals T2x. Okay, now that's important for us. Now, we have the sum of the forces in the y direction. So what forces are acting in the y direction? Well, we have T2y up, so that's going to be a positive T2y. Okay, now we have the weight acting directly down. So that's going to be a minus the weight, and that's it, right? So that will equal 0 because the ball is not moving, so there is no acceleration, so that equals 0. And again, we can solve this, and we have T2y equals the weight. But we know what the weight is up here. The weight is 2,500 newtons. So that means T2y equals 2,500 newtons. And that's great. Now we know the length of this vector right here is 2,500 newtons. And because we know this angle here is 20 degrees, we can use that 20 degrees to figure out the length of T2x. And if we know the length of T2x, over here we figured out that T2x is T1. That was what we were looking for in the first place. We wanted to know the tension in the cable over here, T1. We'll have our answer. So what we want to do now is just use some trig and figure out the length here. So I have this angle, that's my reference angle. I'm looking for the opposite side then, and I know the adjacent side. Opposite side, adjacent side, that's OA, that's TOA, so I need tangent. So I have tangent, my 20 degrees equals the opposite side, which is T2x, over the adjacent side, which is T2y, which is 2,500 newtons. Okay? So I'm just going to solve for T2x before I plug anything in. So I have T2x, which by the way is T1. So I'm just substituting that in right now, equals T2y multiplied on both sides here gives me T2y tangent 20. Okay, so that means T1 equals T2y was 2,500 newtons times tangent 20 degrees. And I can plug that into my calculator and get an answer. And it winds up being, with significant figures, 910 newtons. And that's your answer. Okay, so moving on. We have a rod that is free to slide on a frictionless sheet of ice. So frictionless surface down here. One end of the rod is lifted by a string. The rod is at rest. Which diagram shows the correct angle of the string? We have A, B, and C. Take a second, try to figure it out. Okay, so the correct answer is B. Why is the correct answer B? So you need to start, if you haven't already, you need to start thinking in terms of forces. What forces are acting on these objects, okay? There's a tension in these ropes, or strings, or whatever they are, okay? Obviously, there's a tension acting this way, there's a tension acting this way, there's a tension acting this way. The tension acts along the string, okay? Now, there's a frictionless surface here, so there is no friction force, therefore, acting on the bar, holding it in place, all right? Now, if you break these tensions into components, that means that there's a component acting up, but there's also a component acting that way. So, what's going to happen? Well, the component acting up does nothing. But the component acting left is going to cause the bar to slide to the left. So the rod is not at rest. If I look at C, the same thing is going to occur. There's a component acting up and there's a component acting to the right. So the bar is going to slide to the right. If you look at B, the tension force is acting directly up. There is no left or right component, therefore the bar does not move. Okay? That is a concept question. You have to start thinking in terms of forces and then break them into components so that you can come up with answers. If you aren't doing that, you got to start. Okay, so moving along. The car with a mass of 1,500 kilograms is being towed at a steady speed by a rope held at a 20-degree angle from the horizontal. So we got to try to picture that, all right? A car is being towed. We're at a steady speed. This is critical. By a rope held at a 20-degree angle from the horizontal. Okay, so we're just going to picture that in our minds. We're not going to try to draw a picture of it. We just see it in our heads. And then we're going to go straight to the free body diagram. Now we have a friction force of 320 newtons this time opposing the car's motion. That has to happen because if it doesn't happen, we're being towed. That's going to be a tension force in one direction. If there's no friction force opposing that, then we're going to be accelerating. And that means we're not going to have a steady speed. Okay, so we have to have this balancing force. Now, opposing the car's motion, that's great. We kind of have a visual now of what the free body diagram is going to look like. What is the tension in the rope is the question. We can go straight to the free body diagram. So I'm going to see if I can try to start being a little bit less shaky with my drawings here and start using actual lines. So we have our free body diagram, and then we have our free body, so we draw a nice dot here, and then we move to where are our forces. So obviously we're going to have the weight vector down. Yeah, this is probably not going to work out so good, but we'll see. Maybe I'll get better as we go. Okay, yeah, not good. All right, so weight vector down. Okay, and then we also have because it's on the ground and we have a weight vector down, we must have a normal vector up. Yeah, I don't like that. Okay, normal vector up. Okay, and then those two probably are balancing each other. We really don't know at this point in our physics careers if they actually are balancing each other out or not. So we drew them kind of similar to each other, all right? Now, we know that we have the tension force, and I'm going to draw that tension force in the positive direction, because why not? Make our life a little bit simpler. So we have this tension force. Now, it told us this at a 20-degree angle, so that we do the best we can with the 20-degree angle. Again, hopefully you're making your pictures or your free body diagrams a little bit bigger than you have been. If you have been drawing them small, you have a lot of details you want to fit into these drawings. This is a tension force, so I'm labeling it capital T. I don't have any other tension forces, so I'm just calling it T. It's a vector, so I put an arrow above it. And then we also have this friction force. Now, I don't know what kind of friction force it is, so I'm just going to call it lowercase f. It opposes the motion, and so it goes the other direction, and it's just lowercase f. All right, so now we have three forces that are acting along the axis, and then we have one force that is at an angle. Immediately, I'm going to break that vector into components. I have a tension force that is acting along the x direction, so that is T sub x. And then it is also going to act in the y direction and complete a right triangle, T sub y. All right, so now we have our free body diagram, and we can go straight into the things that we know and the things that we don't know. what do we know? Well, they gave us a mass of 1,500 kilograms, so I'm going to write down M equals 1,500 kg. They gave us a friction force of 320 newtons, so F equals 320 newtons. And that's what they told us. So that's what we know. Now, what am I looking for? What is the tension in the rope? Okay, fine. So T is what I'm looking for. And I like writing that down because if I don't, then I might lose track of what it is that I'm trying to find, okay? So now I'm going to do a sum of the forces. So the first thing I'm going to do is the sum of the forces in the x direction. I don't know why, I just like doing that. So x direction, what do I have? I have T sub x. That's a positive force because it's going in the positive direction. And then minus F because it's going in the negative direction. We are moving at a steady speed. That means F net, which I should put on my free body diagram, F net equals 0. Okay, so F net equals 0. That means we have no acceleration, which means MA equals 0. So F equals MA. We have F, all of our forces here, equals 0. All right, so that's the sum of the forces in the x direction. Now I can solve for T sub x. T sub x equals F. But I know what F is. F is 320 newtons. So this means T sub x is actually 320 newtons. All right, now I'm just trying to find the tension. The tension is here, this vector right here, the hypotenuse of this right triangle, and I already know one side of the right triangle. If I know one side of a right triangle and I'm looking for another side of a right triangle and I know the angle sitting here, I can use trig to find the other. I don't even have to do the sum of the forces in the y direction. I could, but it's kind of a waste of my time. Okay, so I'm just going to go jump straight to, I know the adjacent side of my reference angle. I know I'm looking for the hypotenuse of my right triangle. So adjacent and hypotenuse, that would be AH, that's cosine 20 degrees, equals adjacent side, which is T sub x, over the hypotenuse, which is T. I'm looking for T. So I'm going to have to solve for that one. So I'm going to multiply both sides by T. That gives me T cosine 20 degrees. I'm going to have to divide both sides by cosine 20 degrees now to get T by itself. So I have T equals T sub x over cosine 20 degrees. Now I know T sub x is 320 newtons, so I can substitute that in. I have 320 newtons over cosine 20 degrees, and I can plug that into my calculator. I wind up with T equals 340 newtons after significant figures. Done. So always be aware of what it is that you're looking for and keep an eye out for how can I get there, okay? Right here, we were ready and we did not need to do the sum of the forces in the y direction. Don't be a robot. Always be looking for where you can get to the answer quickly, okay? Robots would just do the sum of the forces in the y direction even though they didn't need to, all right? So we got one more thing to do here and we're done. A ball of weight 200 newtons is suspended from two cables. This is similar to what we just did. One horizontal and one at a 60-degree angle. Notice this, where the 60 degrees is, as shown. Which of the following must be true of the tension in the angled cable? So take a second to think about this, pause the video, and try to come up with an answer on your own, and then we will talk about it. So what is the answer? The answer is actually A. Why, though? That's the important thing. How come? Well, like I said earlier, you have to start thinking in terms of forces. What forces are acting on this ball? So if we just do a simple free body diagram, like maybe even just in your head, what is going on this object? Wow, that was amazing. What is going on this object? It's not even going to erase for me. Okay. Okay, So magic. Now, obviously we have a weight vector down. So I draw in my head the weight vector down, or just on paper, a quick sketch. I have a tension vector this way, okay? Don't know how much. And then we have this tension vector this way, okay? Now, the question you have to ask is this object moving? And the answer, of course, is no, which means the net force is 0. So there must be a balance of forces in every direction, okay? So when I break this vector here into components, there must be a component this way and there must be a component this way. And everything has to add to 0, okay? So this force, horizontally, these two forces have to add to 0, and vertically, these two forces have to add to 0. So the down force and the up force are equal. The left force and the right force are equal, okay? In order for everything to add to 0 and make a net force of 0. Now, if you understand all of that, then you're in pretty good shape. Now, we put these two raspberry sorbet flavors back together to create this tension vector here. That tension vector must be longer than this cable vector over here, okay? The reason for that is we know this arrow is the same length as this arrow, but we know that the hypotenuse of any right triangle is the longest side of any side in the triangle, and this is definitely not the hypotenuse. This one is. So therefore, because this horizontal is the same as this one over here, the hypotenuse, the tension vector here, must be longer than this one over here. And therefore, because this one here is 200 newtons, that's the weight vector, and this one here must balance this one. This one is longer than this one. This one here is longer than this one here. And so by the same logic, this one here is the same length as this one here. So that means that the tension vector must be longer than this one here too, okay? So tension in the cable must be greater than 200 newtons. That must be the answer, all right? So that's how you can kind of figure that one out. It's all just using logic and the balance of forces. So that's it. That's the section.